Welcome to this lecture on reduced order estimator. Why estimate all the states? Let's estimate only the missing ones. Let's develop the estimator by correspondence. Consider our standard state space equation. Suppose we measure XA and XB is not measured, where XA and XB are the same states split into two. We get the corresponding two equations here. So let's estimate only XB. We will use XA as it is. So let's rewrite the second equation as given here. Let us compare this equation with the top equation. In the place of X we have XB. In the place of A we have ABB. In the place of BUK we have this entire term. This table will be used subsequently. Now let us take the first equation. Let us rewrite it as follows. On the left hand side I have all the measured variables. On the right hand side I have the state that is to be estimated. Let us compare this with Yk equals Cxk. And let us notice the following correspondence. In the place of C I have AB. In the place of X I have XB. In the place of Y I have this entire thing, I have put it here. So let us combine these two tables. The set of correspondence we obtained in the previous slide through the first table, and here is the second table. Let us put them together. Let us recall the full order estimator that we derived in the previous week. This was the full order estimator. Let us use the correspondence here. So in the place of X we have XB. We put the hat here as here. In the place of A I put ABB. In the place of LP I use LPB. This is the unknown. In the place of C, AB. In the place of X, I put XB. In the place of BUK, I put this whole thing. Similarly, LP I retain as it is, but put a B here. In the place of Y, I put this whole thing. This is the estimate of XB, so I put a hat here. We obtained this by correspondence. We have reproduced the estimate of XB as given here. Let us rearrange it as follows. The first two terms I retain as they are. Then I write down the term involving k plus 1. So here it is. Next I write XA of k terms as given here. You can see that it comes from here ABA and then LPB AAA as given here with a minus sign. Then I group UK terms. Only XA is measured. Recall that Y is equal to XA because we directly measure XA. Wherever XA is there, we replace it with Y. This depends on Yk plus 1 also, unlike a full order estimator. What we will do is, in the next slide, we will bring this Y of k plus 1 to the left hand side and then write the same expression. So as mentioned earlier, let us rearrange and write down this equation as before. Now let us subtract and add this term as given here. So let us look at the right hand side. So the first term I write it as it is, then this term is added. So I have a minus sign minus LPB Y of k. So I am subtracting first and then I add the same thing. And the last row is retained as it is. Let us group the second and third terms. So the first line is written as it is. So then I write this here, ABA minus LPB AA is given here, multiplied by YK is pulled out, then this term comes here, and then the last term is retained. So now notice I have XB hat LPBY on the left hand side, I also have it on the right hand side, except here it is function of k, on the left hand side it is a function of k plus 1. So we will call this eta and then simplify. So let us define XB minus LPBY, here I am defining it without hat. So this y is equal to XA, so I write the same thing, it is equal to eta, this will be eta hat, this is eta hat at k, this is eta hat at k plus 1, so I get this equation. So this is the reduced order estimator eta hat. So as mentioned earlier, we have defined eta as given here and its estimate with XB replaced by XB hat as given here, and here also XB hat. In the place of y I put XA, it is eta hat. So the error in the reduced order estimator is eta minus eta hat. So if I subtract this, I get XB minus XB hat from here. Let us derive that estimator error, XB minus XB hat. Recall XB, that was the second equation in the first slide, and its estimator that we got by correspondence. Let us subtract to get the estimator error. So when I subtract, I get the first term ABB XB of k and then ABB XB hat of k, which is given here. Then the second term here, so it becomes plus here, and these two terms get cancelled and only the last term appears, so I have a minus sign. So let us reproduce it and recall the measured state equation. This was the first equation in the first slide. So let us substitute this over here. So I retain everything else, only here I have to make a change. So minus LPB, and in this place I put this last term. I have AAB into XB. Now I can group these two. So the first term is written as it is. The second term has, after grouping XB and XB hat, I get this expression. So let us start with this equation. This is what we had in the previous slide, and recall the estimator error definition. So this is error. So you can see that error is present in both the terms. So I get ABB minus LPB into AAB into E of k. This whole thing is E of k. We want the error to go to 0 in the way we want. The question is, can we place the eigenvalues of this term by choosing LPB? We can recall that this is possible if ABB comma AAB is observable. So let us recall the pole placement problem that we had in the previous slide. Suppose XA is a scalar, then XB is of length n minus 1, where n is the length of the state x. Let us use the Ackermann's formula. So we get this familiar expression for LPB. This is the desired polynomial. The control law is given by minus k into x hat of k and x hat has two components, xa and xb, and we are going to estimate only xb denoted by xb hat. So let us recall the estimator, reduced order estimator that we had obtained earlier, and we also measured xa and we called it y. So let us substitute here. So the first term remains as it is. In the place of xa I have put y, and in the place of xb hat I take this to the right hand side and put here eta hat plus LPB into xa of k, but xa is equal to y. So I have got this expression. Y is measured, eta hat is estimated. We can implement this controller. To conclude, we assumed the simple case of measuring a subset of states. We did not measure a function of states, we measured a subset of states directly. We split the equation into state and output equations. We used correspondence. We arrived at an estimate of unmeasured states. We called it xb hat. We built a lower order estimator x hat using xb hat. Estimator error can be made to go to 0 by pole placement. We will present an example in the next lecture. This brings us to the end of this presentation. Thanks for joining. Goodbye.